Today we're blasting off to a very recent but incredibly momentous day in history, December 25th, 2021. For many, it was a day of festive cheer. But for the global science community, it was a day of heart-stopping anticipation. This was the day humanity launched its most ambitious eye on the universe, the James Webb Space Telescope. Let's set the scene. On a Christmas morning at the Guiana Space Center in French Guiana, an Ariane 5 rocket stood ready. Its precious cargo? A $10 billion observatory, folded up like a delicate piece of origami, waiting to begin a journey of 1,000,000 miles. This wasn't just another satellite launch. This was the culmination of decades of work, involving thousands of engineers and scientists from NASA, the European Space Agency, and the Canadian Space Agency. The stakes were astronomical, literally. The James Webb Space Telescope, or JWST, is often called the successor to the Hubble Space Telescope. But that doesn't quite do it justice. While Hubble has given us breathtaking views of the cosmos, primarily in visible and ultraviolet light, Webb is designed to see the universe in infrared. Why is that so important? Well, think of it like having a superpower. Infrared light can pierce through a cosmic fog of gas and dust that obscures Hubble's view, revealing the birthplaces of stars and planetary systems. But even more profoundly, JWST is a time machine. The universe is expanding, and as light from the most distant galaxies travels across billions of years to reach us, its wavelength gets stretched out, shifting it into the infrared spectrum. This is called cosmological redshift. Webb's incredible sensitivity to infrared light means it can see this ancient stretched-out light. It can look back in time over 13.5 billion years to witness the very first stars and galaxies flickering into existence after the Big Bang. It's an astronomical holy grail scientists have dreamed of for generations. To achieve this, the telescope is an engineering marvel unlike anything ever built. Its primary mirror is a staggering 6.5 meters, or 21 feet across. That's nearly 3 times the size of Hubble's. A mirror that big couldn't possibly fit into a rocket, so it was designed as 18 individual hexagonal, gold-coated beryllium segments that would have to unfold and align themselves perfectly in space, with a precision of a fraction of the width of a human hair. And to see that faint, ancient infrared light, the telescope has to be incredibly cold. Any heat from the sun, Earth, or even its own electronics would blind its sensitive instruments. The solution: a 5-layer tennis court-sized sunshield. Each layer is thinner than a piece of paper, made of a material called kapton, and coated with aluminum and silicon. This shield is designed to keep the telescope's optics at a mind-bogglingly cold -233 degrees Celsius, or -388 degrees Fahrenheit. That's just a few tens of degrees above absolute zero, the coldest possible temperature in the universe. The launch itself on December 25th was just the beginning of what engineers called 30 days of terror. There were over 300 single points of failure, hundreds of individual steps that had to go perfectly for the mission to succeed. The telescope had to unfold its solar array, deploy its antenna, unfurl that massive sunshield, and then meticulously assemble its mirror. It was a complex, automated ballet happening 1,000,000 miles from any human help. If any one of those steps failed, the entire $10 billion project could become the world's most expensive piece of space junk. Imagine the tension in mission control at the Space Telescope Science Institute in Baltimore. For weeks, they watched telemetry, sending commands and holding their breath as each motor, latch, and pulley did its job. First, the sunshield deployment. The covers rolled back, the booms extended, and slowly the 5 massive layers were pulled taut, one by one. Each successful step was met with applause and relief, but the tension remained. Then came the mirrors. The secondary mirror swung into place on its tripod. Finally, the 2 side wings of the primary mirror, each holding 3 segments, folded forward and latched, completing the iconic hexagonal honeycomb shape. On January 24th, 2022, a month after its Christmas launch, Webb successfully fired its thrusters to enter its final orbit around a point in space known as the second Lagrange point, or L2. This is a gravitationally stable spot about 1,000,000 miles from Earth, where the telescope can keep the sun, Earth, and moon at its back, allowing its sunshield to protect it continuously. It had made it. The deployments were flawless. The journey was a success. But the work wasn't over. For the next 6 months, scientists and engineers embarked on a painstaking process of aligning those 18 mirror segments. They had to be adjusted with nanometer precision to act as a single perfect mirror. They focused on a single star, HD 84406, and carefully moved each segment until the 18 separate images they initially saw merged into one single, razor-sharp point of light. The first alignment images that came back were stunning, sharper, and clearer than anyone had dared to hope. The telescope was working, and it was working perfectly. Then, on July 12, 2022, the world got to see what Webb was truly capable of. NASA released the first full-color images and spectroscopic data. The first image, Webb's first deep field, was an instant icon. It showed a galaxy cluster called SMACS 0723. In a patch of sky the size of a grain of sand held at arm's length, Webb revealed thousands of galaxies, some of the most distant and oldest we've ever seen. The gravity of the foreground cluster was bending and magnifying the light from galaxies behind it. An effect called gravitational lensing, giving us a warped but magnificent view into the deep past. The images kept coming. The stunning cosmic cliffs in the Carina Nebula, stellar nursery where we could see brand new stars emerging from their cocoons of gas and dust for the first time. Stephan's Quintet, a group of 5 galaxies, imaged with a clarity that revealed shockwaves and tidal tails as they interacted and merged. The Southern Ring Nebula, the dying breath of a star, where Webb revealed not one, but 2 stars at its center. And it didn't just take pictures. Webb's instruments analyzed the atmosphere of an exoplanet, WSPA 96b, and for the first time, found the clear signature of water vapor as well as evidence of clouds and haze. The launch of the James Webb Space Telescope on December 25, 2021, wasn't just a technological triumph, it was a gift to humanity. A gift of knowledge, of perspective, and of wonder. In its short time in operation, it has already begun to rewrite textbooks and challenge our understanding of the early universe, of how stars are born, and of the potential for life on other worlds. It's a testament to what we can achieve when we collaborate, when we dream big, and when we dare to build something that pushes the very limits of our ingenuity. As we look up at the night sky, we now know we have a powerful new eye looking back, peering into the dawn of time, and its journey is really just beginning. What will it discover next? We can only watch in awe. Thank you so much for joining us for this look back at an incredible day in recent history. If you enjoyed this journey into space, be sure to hit that like button, subscribe for more stories, and let us know in the comments what you think is the most exciting thing about the James Webb Space Telescope. We'll see you next time.